afternoon, everyone. Okay, so we have a small talk today. Maybe the rest will watch the recording later or what. Okay, so we will go ahead and start. All right, so today's session is revision questions. All right, so we have quite a lot of questions to go through. Okay, again, I hope you read through Prof. So's email. Okay, for this Saturday. So again, please make sure you come prepared, come early. All right. Yeah. And bring your calculator and all your material. Okay. So let me get started. All right. So we don't get dragged for too long. Okay. So all these questions that we are going through are all actually questions from the past semesters assessments. All right. So these are the type of questions that have been asked before. Okay. So you get a feel of how it has been like. Okay. So let me go through the questions. All right. And as before, I'll just go through. Okay, if you have any questions, anything you're not sure, you can stop me. All right. If not, I'll just go question by question. All right. So the first few questions are on the transformers, all right, and the diode bridge rectifier. Okay. So in this first question is about a transformer where we are given the currents in the primary and secondary. All right. So basically, what we are given is IP is 14 ampere. And IS is 2 ampere. So the relationship, okay, we know, okay, NS over NP equals to IP over IS, it should be 14 over 2. All right, so NS will be equals to 7 times 120, which should be 840. Okay, so the answer here. Okay, so some of the questions are quite straightforward, quite easy. All right, so you don't need to really think too much. Okay, question 2. So we have a full wave rectifier connected to a resistive load with a load voltage of 8 volts. Okay, if the ripple voltage is 0.4 volt peak to peak, calculate the filter capacitor that is supposed to be connected. Okay, so if you remember from your studio, okay, so you built your full wave rectifier. Okay, so this is your full wave rectifier that you built. All right, then of course before that is your transformer, and from here you connected up your capacitor and your resistor. This is your load, okay, RL load. Okay, and what we are saying is your VL, in this case your VL is 8 volt. Okay, your delta V is 0.4. Your resistors here is 20 ohms. Okay, and your frequency of the signal here is 60 hertz. Okay, so you have all this information, correct? So all you need to do is just put it into the formula, all right, that is given to you, okay, from your handout. So the delta V is approximately VL over RL times 1 over 2Fs times 1 over C. Okay, so you'll get 0.4 equals to 8 over 2, 20, 60, and C. So you get C is 8.3 microfarad. Okay, it is this. Okay, so it's just a matter of applying all the values to the formula. Okay, question 3 is a transformer question. So you have primary voltage 200 VRMS and power, okay, at the primary side, okay, is given as 1200 watt, and the current at the secondary side is 1.5 ampere. So they asked to calculate the number of turns, the secondary voltage, okay, secondary voltage. So for a transformer, we always assume that the input power is equal to the output power, right? So if input power is 1200 watt, this also implies that the output power is also 1200 watt. Okay, and we know the power is IB, so it's 1.5 multiplied by Vs. So Vs will be equals to 1200 over 1.5, which will give me 800. Sorry. Yeah. Okay, you give me 800 VRMS. Okay, so that is your question 3 here. Okay, question 4 is similar to question 2. All right, so the same sort of parameters are given, and you just need to plug it in. So delta V is VL over 2 FS RC, which will be 0.9, will be equal to 12 over 2, 50, 40, and C. So C will be 3 microfarad. Okay, so it's the exact same sort of type of question from question 2. Okay, question 5 is very similar to just now question 3. All right, so we know that the secondary power, okay, is 1500 watt. Okay, so which means that the primary power is also 1500 watt. Okay, and since we know that the voltage at the primary is what we want to find, so Vp multiplied by the primary current 12.5. So Vp will be equals to 120 volt RMS. Okay, D. Okay, so it's the same approach as your earlier question. So the key thing is that the transformer's power is equal on both sides. So when we know that input power is or the output power is 1500, so the input power is also 1500. Okay. Question 6 is again on transformer. Okay, so you're given all this information. Your primary current is 4, your secondary current is 28, your number of turns in primary is 100. Then you just put it into the formula, correct? NS over NP is IP over IS. So NS will be equals to 4 over 28 times 100, 14.3. So that will give you approximately 15 turns. Okay, your answer here. Okay, so that sort of wraps up the first few questions on the transformers. All right, so the next few questions are all on the motors. All right, so these questions generally are a bit more tedious. All right, there is more steps involved, more working involved. All right, but as long as you see what is the information given and what I need to find out, then you see that it's sort of consistent in the way we approach it. Okay, so the first question here. So we have a motor connected to a 12 volt source. So we have a 12 volt source here connected to a motor. Okay, so we know that this is 12 volt. Okay, this is your R, and this is your back EMF voltage that you will generate. Okay, under no load condition, the motor speed is 1000 RPM. Okay, so the information is under no load. So when you say no load, we say is at 1000 RPM. Now, when you say no load, what does that mean? All right. So if you remember from the tutorial, no load basically also means that your current is 0. All right. So it is sort of free spinning. All right. With 0 current. All right. So with that, we can say that your back EMF voltage here is equivalent to your source voltage. Okay, because if there's no current, then there's no voltage drop across the resistor. So whatever voltage that you're applying at the supply is equivalent to the voltage seen as the back EMF. So EB, all right, so you can say that EB will be equals to, which is K omega is actually equals to 12. All right, with that you can go ahead to find K. So omega is 1000 RPM. So you convert it to 2 pi over 60 equals to 12. So you'll find that K is 0.1146. Okay, so that is the first step. You find this K value. Okay, so next you want to find the resistance. You want to find the resistance. And to find this resistance, you must have a case where current is flowing. All right, so that is why we now have the second scenario, which is we have a load torque of 1000 Newton meter and the speed drops to 900 RPM. Okay, the speed drops 900 RPM. So now what we can say is at 900 RPM, okay, at 900 RPM, what is happening is you can now calculate a new back EMF voltage. All right, EB is equals to K omega. So this will be, so you substitute the K value here, is 0.1146 multiplied by omega, which is 900 times 2 pi over 60. You will get a back EMF of 10.8 volt. Okay. Next, you also, since you already know K, okay, and you know the load torque, you can use this expression that torque is Ki. Okay, with that you can find your I, which is 8.726 ampere. Okay, because torque is 1, all right, and K is your 0.1146, so you can find your I. So once you find your I, so you know this I value, you know the back EMF, and you know the source voltage. So it is about putting a loop over here. All right, so you can say that V is IR plus EB. So 12 volt is your 8.726 multiplied by R plus your 10.8. Okay, so with that you'll be able to get your R value 0.138 ohm. Okay, so if you look at most of the questions, they have a similar sort of pattern. That means they will give you a first scenario to find some unknown, and then there will be another sort of scenario to find the actual answer. All right, so you need to sort of relate the first step and the second step to know, okay, what I need to find, what is missing, and then I move on to find the actual answer that the question is asking for. Okay, so yeah, so at the end of the session, I will, as usual, upload the video and I'll also send you all this writing that I'm doing, okay, as PDF file, so you can refer to that. Okay, question 8. A permanent motor is connected to a 24 volt DC source. So under no load condition, the motor speed 2000 and then a load torque of 1 Newton meter, speed drops. Okay, so you can see that it's sort of similar. All right, you are given first some information, all right, and then another situation, and then you're asked to find some unknown. All right, so let's look at what is given first. So first we know that under no load condition, we are running at 2000 RPM. Again, as we saw just now, under no load means your current is 0. So your back EMF voltage is equals to your source voltage, which is 24. Okay, so K omega is 24. So K multiplied by omega. Okay, then you can find your K 0.1146. Okay, and then we look at the next step. So the next step, what is given? At 1 Newton meter, the speed drops to 1800 RPM. Okay, so the first thing is we can find the current. Okay, so we know that torque is Ki, so I is equals to torque, which is 1 over K, 0.1146, which will give me 8.726 ampere. So that is the current that is going to flow through in this situation here. Okay, at 1 Newton meter torque. Okay, and at 1 Newton meter torque, you can also calculate the back EMF voltage. All right, so the back EMF voltage will be equals to K omega, which will be 0.1146 multiplied by omega. In this case, it is at 1800. Okay, 21.6 volt. Okay, now once I calculate the current and I know the back EMF, okay, at this particular situation, then I can already calculate the resistance. Correct. So the resistance is basically drawing the loop. So we know that B is IR plus EB. Okay, so the source is 24 volt goes to 8.726 multiplied by R plus 21.6. So your R is 0.275 ohm. Okay, so now we have all these parameters, correct? We have all these parameters, and if I were to draw it now, so I have your motor, your resistor, I mean your source, your resistor, and your motor here, correct? And we already know that this is the resistance 0.275 ohm. And now what is the last part? The last part is, suppose we wish to operate the motor at the speed of 1600 RPM for the same load torque. Okay, so the load torque, if you look at the formula, load torque is equivalent to Ki. All right, so if the torque is the same, K is constant, it means that the current is the same. All right, there is no change in the current. That means I'm still having the same 8.726 ampere flowing through. Okay, and what I want is, I'm now going to operate the motor instead of a fixed DC source. I'm going to operate it with a PWM with the on voltage of 24 volt. Okay, on voltage of 24 volt. And what is the duty cycle? All right, so basically now what I need to do is, I need to find out, okay, how much is the voltage I require here. Okay, how much is this voltage that I require such that I'm able to have 8.726 ampere of current flowing through with this motor. All right, and with the back EMF based on this required RPM of 1600. All right, so I put it back into the same formula here. V equals to IR plus EB, but now I'm actually trying to find the V. Okay, so the current is 8.726 multiplied by the resistance, which is 0.275 plus EB. So EB is K omega. So K is 0.1146 multiplied by omega. Omega in this case is 1600. Okay, and that will give me a value of 21.6 volts. Okay, that means what? That means I need 21.6 volts here. Okay, to make sure that I'm able to operate the motor with the same load torque. Okay, running at 1600 RPM. Okay, now the thing is, this 21.6 is actually a PWM signal, correct? So we know as a PWM is on and off, correct? And we know that this on voltage is 24, this will be 0. Okay, so what we want is to calculate the duty cycle. So duty cycle is basically on time over off time. All right, so it is equivalent to saying the ratio of the voltage that you want over the total voltage. Okay, so the duty cycle, okay, is actually calculated as 21.6 over 24 times 100%, which will give you 90%. Okay, so with the duty cycle of 90%, okay, I will be able to generate equivalent voltage of 21.6 volt, which is what I require here. Okay, so that's why the answer here is B, 0.9. Okay, so that is this question. Okay, so like I said, usually these motor questions are the more tedious ones, all right, because there are a lot of steps involved. All right, so you just need to make sure you follow through the steps carefully, okay, when you are trying to solve the question. Okay, question 9. So we have a motor with a 12 volt supply. So under no load, the motor speed is 2500 RPM. All right, so it's again similar approach. All right, so we will take the first scenario first. So under no load condition, we know it's a 2500 RPM. And as we have already seen under no load, we say that EB is equals to K omega, which is equals to, in this case, your 12 volt. Correct. So we can say that 12 is equals to K multiplied by 2500 times 25 over 60. So I can find K to be 0.0458. Okay. Now the next thing you are told is the shaft is clamped mechanically such that it doesn't spin. Okay. And the current drawn by the motor is 0.5 ampere. So now the scenario is a bit different. We say it's a stall condition. So under stall condition, the motor does not spin. If the motor does not spin, your back EMF is equivalent to 0. Because your omega is 0, correct? If it doesn't spin, your omega is 0, so your back EMF is 0. So with that situation, we know that the current drawn by the motor is 0.5. All right, so we can just do Ohm's law to say that the resistance will be 12 over 0.5, which will be 24 ohm. Okay, why? Because in your circuit, okay, now you originally have a resistor and your motor, all right, but now we say that there is no back EMF, so this is equivalent to 0 volts. Okay, so the only thing in the circuit is your source, which is the 12 volt here, and your resistor here. Okay, so now we can calculate the R. And what is the last step? When a particular load is attached to the shaft, its speed drops to 2000 RPM. So the current run by the motor for this load torque is how much? So we can calculate the current, okay, based on the formula that we have, IR plus EB. Right, so we know that the voltage is 12, okay, and we want to find the current, and we already know the resistance plus the back EMF is through the K omega 0.0458, and the omega is 2000. Okay, so with that you can calculate I to be 0.1 ampere. Okay, so it's again quite similar, all right, in a sense that we always find K first, and then after that we look at what other information is given, and then we try to solve. Okay, question 10. So in question 10, we are given that a PWM control motor powered by a 12 volt supply. The torque is 30 milli. The motor drives a top load at a speed of 2000 RPM, 90% duty cycle. Okay, so in duty cycle now you 60%. Will the load remain, while the load remains the same, what will be the speed? Okay, so let's look at what is the information we have. So we know that V is 12 volt. All right, the torque constant K is 0.03. So we already given K. Okay, so we know that the supply is 12 volt, but we're using a PWM running at 90%. Okay, so 90% duty cycle basically means that is 0.9 of 12 volts, which will give me 10.8 volt. Okay, and at 10.8 volts, we are able to drive the motor at 2000 RPM. Okay, so if I put this into my expression, V equals to IR plus EB, so I'll get 10.8 equals to IR plus EB is K omega, so 0.03 multiplied by omega, 2000 times 2 pi over 60. So with this, I'll get IR is 4.517 volt. Okay. All right. So now we have an expression for IR, which is 4.517 volt. Okay. So we don't know what is I. Okay. We don't know what is R. All right. But since the load is the same, all right, because in the second part, the load remains the same, which means that the current remains the same. All right. If the load torque is remaining the same, that means the current remains the same. So the IR will also be the same. Okay. So we don't need to individually find I or R. Okay, so what we know is in the second part we have reduced the duty cycle to 60%. Okay, so at 60% duty cycle, what you have is 0.6 times 12, which will give me 7.2 volt. All right, then I put in the same expression, V equals to IR plus EB. So 7.2 is equals to 4.517 plus EB. So EB will be equals to 2.683, which is equals to K omega. Okay, and since EB is K omega, with this I can go back and find omega to be equals to 2.683 divided by 0.03. Okay, that will give me 89.4, but that is radians per second. So I need to 89.4 multiplied by 60 over 2 pi, which will give me 854 RPM. Okay, it is this. Okay. So the next question. Okay, so in this next question, we are given that the voltage is 24 volt. So when the motor current is 0.4 ampere, the motor spins at 3000 RPM. So when I is 0.4, we know we're running at 3000 RPM. Okay, when the current is 0.8, we're running at 1200 RPM. Okay, so what is the torque constant of the motor? Okay, so what we can do is we can put it into our expression that we know. So we know that V is IR plus EB. So 24 is equals to 0.4 multiplied by R plus K omega. So it will be 3000 times 2 pi over 60. Okay, so that's the first expression. Now the second expression will be 24 will equals to 0.8 of R plus K 1200 times 2 pi over 60. Okay, so you have expression 1 and you have expression 2. Two expressions with two unknown. All right, and you're supposed to find the K. All right, so you can do simultaneous equation, correct? To say that if I take equation 1 multiplied by 2 minus equation 2, then what I will eventually get is R is eliminated. So I only have K. Okay, then if you go ahead to solve, you'll get the answer here. Okay, so in this, we are doing simultaneous equation to eliminate the R and just so they were just left with K. Okay, question 12 is about what is the current drawn when you're providing maximum power. All right, so if you look back at our Thevenin's theorem, correct? We say that when we reduce a circuit to a Thevenin's equivalent, maximum power is when RT is equals to RL, which means that the voltage across RT will be equals to the voltage across RL, correct? Because it's divided by 2. Okay, so equivalently, if I have a same situation with a motor, so I have a voltage source and I have a motor and I have a resistor and a motor. Okay, whatever voltage here, I have maximum power delivered if the voltage is equally divided. So that's maximum power transfer. That means if my source is 24 volt, okay, if my source is 24 volt, then here must be 12 volt and here must be 12 volt. All right, and since we know the current, the resistance is 2.5, so the current will be 12 over 2.5, which is 4.8 ampere. Okay, so that sort of wraps up all the motor based questions. Okay, so now we're going to go on to the op-amp questions. Okay, so let's look at this circuit and we are asked to find the value of I out. Okay, so for me to know I out, I must know V out, correct? So usually what we will do is always go back to the op-amp golden rules, all right, and then apply whatever node analysis and Ohm's law, whatever, or KCL, okay, that we can apply to eventually find what we want. So in our case, we want to find V out. All right, so I need to trace V out, or I need to find, come up with an expression that has V out in it so that I can solve for it. All right, so since V out is here, I can say that V out is also here. All right, it's the same line that is connected. Now, if I look at this point here, okay, since we know that based on op-amp golden rules, there is no current flowing into the op-amp. So from this 10 volt supply, all I have is 8K and 2K. That means this voltage here is a voltage divider, right? 10 over 2 over 10 multiplied by 10, okay, which will give me 2 volts. So this point here is 2 volt. All right. So if V plus is 2 volts, then the other golden rule is V plus equals to V minus. All right. So this is also 2 volts. All right. So far what you've applied is, we know V out is connected to this point here. So that is also V out. All right. And at the positive terminal is just a voltage divider. So the voltage at the V plus terminal is 2 volt, which also means that the voltage at the V minus terminal is also 2 volts. Okay. Now, in order for me to find some expression, okay, I need to apply KCL or node analysis. All right. So what I can do is I can sort of declare this node, okay, to be VA, and then come up with some expression that relates V out and VA together, and then try to solve for the V out. Okay, so again, we are going back to many of the first principles that we studied before. All right, it's the same thing. So when we create a node, we can say that all the current flows in or flows out. Okay, that is your KCL. So I can say that all the current flowing in or flowing out can be equal to 0. Okay, so if I say all the current flowing into the node VA, then I can have the expression that says 8 minus VA over 2K, which is this line over here, okay, plus V out minus VA over 2K, which is this line here, and then this line will be plus 2 minus VA over 2K equals to 0. Okay, so I can say that is going to be my first expression. For the second expression, I can do the same thing. I can say that all the current flowing in can be 0. And since there is no current flowing in the terminal directly connected to the op-amp input, we can leave out that branch. Okay, so basically you only have 2 branches here. So I can say that VA minus 2 over 2K plus V out minus 2 over 2K equals to 0. Okay. Now, with that, I can sort of simplify this expression to say that VA is equals to 4 minus 4 minus V out. And I take this and I put it back into expression 1. Okay, so when I do that, I will be able to simplify and say 10 plus V out minus 3 VA equals to 0. And eventually, when I solve, I'll get V out is 0.5 volt. So if V out is 0.5 volt means this voltage here is 0.5 volt. Okay, so the current flowing through, okay, the I out will be 0.5 over 2K, which will be 0.25 milliampere. Okay, so let me move on. Okay, question 14. So it's another op-amp. Okay, so we are always going to apply all the rules that we know, okay, to solve it. And we're supposed to find the value of V out, okay, the value of V out, which is here. All right, so let's go ahead to look at what we know, all right, to solve this step by step. Okay, so for this bottom of M, we know that the positive terminal is connected to ground, which means that this point here is also 0 volt, correct? V plus is equals to V minus. Okay, and we know that for this first op amp here, the positive is connected to 1.5 volt, which means that this point here is also 1.5 volt. All right, so that is what we can straight away see, all right, from the circuit. Now the next thing is, since this 1.5 volt, I can say that this current here, okay, is equal to 1.5 over 1.2K. Okay, so that is the current flowing through that branch over there. Okay, now the next thing is, since there is no current flowing into the input of the op amp, this same current I is also the same current that is flowing through this 3.6K resistor. So it's the same I. Correct, the same I. So we can say that this point here, okay, this point over here, the voltage here will be whatever voltage that I'm starting off at, which is 1.5, plus the voltage drop across the 3.6K resistor. So it will be 3.6K multiplied by the current, which is 1.5 over 1.2K. So that will give me 6 volt. Okay, so this is basically applying Ohm's law. So let me just draw it separately so you can see it. So what I'm saying is, I have a 3.6K resistor here, and I have another resistor here. Okay, and what we know is this point here is 1.5 volt, and I know that this current is I. Okay, and since there is no other branch for the current to flow, it is the same current here. Correct, and since V is IR, the voltage drop across here, V is equals to this I multiplied by 3.6K. Okay, so if I were to take the total voltage at this point here with respect to ground, it will be 1.5 volt add with this voltage drop across the 3.6K resistor, which will give me the voltage on top of the 3.6K ohm resistor. Okay, so that is how I get the 6 volts over here. Okay, so now we know that this point here is 6 volts, and the point at the other end of this 8.2K resistor is 0 volts. Okay, so we can say that I can use this to calculate the current flowing in this branch here. So this current here will be 6 over 8.2K. Okay, and since we know that there is no current flowing into the internal of the op amp, this current I, okay, so maybe I'll call it I1. This same current I1 is going to be the same current that is going to flow up towards the V out. Why? Because there is no other place for the current to go. It can't go into the op amp, so it can only go up towards V out. Okay, so we are going to apply the same thinking as just now. That means at one point we have 0 volt, and then we go through a resistor which is 4.1K, and we want to know what is this voltage here. Correct? And since I know this current is I1, so the voltage at the other end will be the IR, which is I1 multiplied by, okay, so it will be 0 minus I1 multiplied by 4.1K. Okay, is the voltage on top, subtract the voltage drop across the resistor, which will give me the voltage at the other end of the resistor. Okay, so with that understanding, we can actually solve for V out to say that it will be equals to 0 minus this I1, which is 6 over 8.2K, multiplied by the resistor 4.1K, which will give me minus 3 volt. Okay, so let's move on. So this next question here on op amp. Okay, so here we have op amp where the input is a sinusoidal waveform. Okay, so of course when you do the analysis, you just keep it as V in, all right, until the last part that you substitute in. Okay, so that will make it easier, and you don't need to write that full expression all the time. Okay, so let's again look at the circuit and apply the golden rules to see what we can figure out. So the same thing as before, we can see that this voltage here, okay, this point here, okay, will be a voltage divider because there is no current flowing into the input terminal of the op amp. That means this voltage here will be a voltage divider, which is 2.2 divided by 2.2 plus 6.8 multiplied by 9, which will give me 2.2 volts. So here I have 2.2 volts, which means that V plus is 2.2 means V minus is also 2.2 volts. Okay, so we have V plus and V minus. Next is we can have an expression for this current I. Okay, so we can say that this current, okay, so let's call this I1. So we can say that I1 will be V in minus 2.2 over the 4.7K. Okay, now we also know that since no current flowing into the negative terminal of amp, whatever current is flowing in I1 is actually the same current over here in I2. Okay, the same current I2, which means that I2 will be equals to 2.2 minus V out over 8.2K. Okay, and we know that I1 is equals to I2. Okay, so with that you can go ahead to simplify and solve it. Okay, then eventually what you'll get is V out is equals to 2.2 minus 8.2K multiplied by V in minus 2.2 over 4.7K, which will give me 2.2 minus 2.62 cosine 100t. Okay, now if you look at this answer, it doesn't match any of the options here. All right, so that is where you need to go back and see how the waveform can be manipulated. All right, so if you draw out your cosine waveform, okay, so a cosine theta bar right looks like this. Okay, this is your cosine theta. If I were to do a negative cosine theta, is the opposite. Correct. And what do you see? If I have a negative cosine theta, and if I shift it by 180 degrees, you shift it by 180 degrees, then this portion here, this portion here is the same as this portion here. Correct. That means a negative cosine plus at plus with 180 is equivalent to cosine. All right. So that is how we can change this. From negative, change it to a positive, and then you add 180. Okay, so that will give you the answer of A. Okay, question 16. So question 16, we are given two op amps. Okay, so we will apply the same principles that we know. So V plus for the first op amp is 3 volt, which means that here is 3 volt. V plus for the second op amp is 2.2, so this will be 2.2 volt. All right. So what you want to find is VB. Okay. So to find VB, we know that since the voltage, we know the voltage across the 5 ohm resistor, so we can straight away say that this current here, I is equals to 3 minus 2.2 over 500. Okay, which should be giving me 1.6 milliampere. Okay, and since the current, no current flows into the negative terminal, this current is the same current that flows out towards VB, and VB is 2.2 volts minus the voltage drop across the resistor. So VB will be equals to 2.2 volts minus IR, which is 1.6 milli multiplied by the 2K. So that will give me minus 1 volt. Okay, so this is the same as before. So the voltage at any point is, you can take the voltage at the other end of the resistor, subtract the voltage drop across this resistor to know your current voltage value. Okay, so that is how you get your minus 1 volt here. Okay, question 17. Okay, so in question 17, what op amp is supplied with dual power supply? Okay, so one of the things you will notice in question 17 is this first op amp here is actually operating as a comparator. Why? Because there is no feedback. Okay, there is no feedback loop. So when there's no feedback loop in the op amp configuration, that means the output is not connected back to the input, then basically it is a comparator where the output is either based on V plus greater than V minus or V plus smaller than V minus. Okay, so what you want to do is you want to find out what is the voltage that we get. Now, if you look at this op amp over here, the second op amp, you will see that this is actually a inverting configuration. All right, so this is actually negative RF over RI, which is 10K over 10K multiplied by the input 4. So this will be negative 4 volt. Okay, it is an inverting amplifier. Okay, so the voltage at the output of the first op-amp will be negative 4 volt. All right, now the next thing is since we know that no current flows into the internal of the op-amp, when I look at this part of the circuit, what do I observe? So if I were to draw it, you see that I have negative 4 volt here, 10K, and this is the point to the op-amp, and then another 10K and ground. Okay, so this is basically a voltage divider, correct? So if this negative 4, that means this point here will be negative 2 volts. Okay, the voltage divider. So here will be negative 2 volts. Okay, so for the first op-amp, there is two inputs. One is a 1 volt, the other is a negative 2 volts. All right, so which means that your V plus is greater than your V minus, correct? This is your 1 volt greater than your negative 2 volt. So that implies that the output will be positive V set, which is plus 5 volt. Okay, next question, question 18. Okay, calculate the value of I out. Okay, so to know the value of I out, I need to know this voltage here, correct? So, so to get to that, let's start with what we already know. So again, this point over here is similar to the earlier circuits. It's a voltage divider, so it will be 200 over 200 plus 100 multiplied by 6. That will give me 4 volts. So this point here is 4 volts, which also means that this point here is 4 volts. All right. So with that, I can calculate the current here. So this current here will be 4 minus 2 over 100K, which is 2 over 100K. Okay, that is the current there. And since no current flows into the negative terminal of the op-amp, it is also the same current that is going to flow here. Okay, 2 over 100K. Okay, and the same technique as before. So we know this is the point here. So let me call this B. Okay, so let me call this B out. Okay, so we can say that this is B out. Okay, and then I have a 200K resistor, and the other end of it is 4 volt. Correct, and the current is flowing here, and I know this current to be 2 over 100K. Okay, so the voltage at V out would be equals to 4 volt plus the voltage drop across the resistor. So 200K multiplied by 2 over 100K, which should be equals to 8 volts. So V out is equals to 8 volts. So if V out is equals to 8 volt, then the current I out will be equals to V out over 600 ohms, which will give me 13.3 milliampere. Your answer here. Okay, question 19. Calculate the value of V out in this figure. Okay, so we have a dual power supply. So let's do the same analysis. So V plus is connected to ground, which means that this point here is also 0 volts. Okay, if that point is 0 volt, then I can say that this current here I, okay, is equivalent to 3.2 over 500, which will be 6.4 milliampere. Okay, and the same 6.4 milliampere is going to flow here. Okay, because no current is going to flow into the negative terminal of op-amp. All right, now as before, since we know the voltage at this point is 0 volt, after I pass through the 1000 ohm resistor, the voltage at V1 will be equals to 0 minus the IR, which is 6.4 milli multiplied by 1000, which will equals to negative 6.4 volts. Okay, so the voltage at V1 is negative 6.4 volt. Okay, so since we know the voltage there is negative, so we can say that here the current is going to flow in this direction. So here the current here will be I, which will be 0 minus 6.4 over 800, which will be 8 milliampere. Okay, so you can see that at this branch V1, okay, at this node V1, sorry, we can have 6.4 milliampere coming in from the left, 8 milliampere coming in from the bottom up. Okay, which means that all this current is now going to flow out in this direction towards V out. Okay, so I mean this current here will be 6.4 plus 8, which will be 14.4 milliampere. Okay, so 14.4 milliampere flowing in this direction towards V out. So V out will be whatever voltage that there is at V1 minus the voltage drop across the 400 ohm resistor. Okay, so your V out is going to be V1 minus your IR, which is your 400 ohm resistor. So that will be negative 6.4 minus 14.4 milli multiplied by the 400 ohm resistor. So that will give me negative 12.16 volt. Okay, so that wraps up all the op-amp based questions. Okay, so now we'll move on to the filter design. Okay. So some of these questions are very similar. All right, so I think once we do one, you'll see that they are very similar in their approach. Okay, so in this first question, we are supposed to design a band pass filter, okay, with cutoff frequency of 1200 and 4500. Okay, so what do we want to design? We want to design a band pass filter. So you have a lower cutoff and a higher cutoff. So the lower cutoff here will be 1200 and the higher cutoff will be 4500. Okay, now you have to always remember that this is actually your cutoff for the high pass filter, and this is actually the cutoff for the low pass filter. Okay, because the high pass filter's response is always like this, and the low pass filter's response is always like this. Okay, so when you design a band pass filter, the high pass filter cutoff comes first, then the low pass filter cutoff comes later. All right, so all you need to do is to plug in the formula, which is the same, where we say that 1200 is equals to 1 over 2 pi r, and in this case the okay, so in the circuit over here, we must also remember that your RC in this configuration is your low pass filter, and your RC in this configuration is your high pass filter. Okay, so in this case 1 over 2 pi RC. So in this case the C is your 1 nanofarad. Okay, so you can find your R to be no, sorry, yeah, so this is the 1 nanofarad of the high pass filter. So your R, so in this case you're finding R2. Okay, R2 is going to be 132.6K. Okay, similarly over here it will be 4500 is equals to 1 over 2 pi R1 and 100 nano. So your R1 is going to be 354 ohm. Okay, so that's how you get the answer here for B. Okay, so it's the same formula. Okay, as long as you know which one is R and C for low pass and high pass. So this is the exact same question, different numbers. So this is your low pass filter. All right, this is your high pass filter. Okay, and we just apply the same formulas. All right, so the frequency for the high pass filter is 600, which would be 1 over 2 pi 22 nano, and R2, which means R2 is going to be 1206 12.06. Okay. Okay, and your frequency for your low pass filter is 1600, which will be 1 over 2 pi 100 nano. Okay, and R1. So R1 is going to be 995 ohm. Okay, so that's how you get your answer here. Okay, so it's the same as above. Okay, same as the earlier question, only take different numbers. Okay, question 22. Okay, we are going to design a filter. All right, and what we need to know is what is the frequency range we want, what is the frequency range you want to remove, and where is the starting point, and how much we want to remove it from. Okay, these are all the important things that we need to know. Okay, so if you want to draw out this spectrum, so the frequency range of what we want is somewhere here. Okay, so it's around 195 to 395. Now the noise that is interfering is somewhere here. So it's around 4000 to 6000. And what you want to design is, you want to design a filter that can reduce this noise by at least 18 dB. Okay, that means the starting point of the noise, which is 4000 hertz, must be reduced by at least 18 dB. Okay, so if I want to draw the response curve, okay, of the filter, what I want is something like this, where it tapers off, all right, to a point where if I take this point here and I take this point here where it touches the 4000 hertz, this difference should be at least negative 18 dB. Okay, so that is the kind of filter that I want to design. That means when I hit 4000 hertz, I must have reduced the signal by at least 18 dB. Okay, so once you know these numbers, then it's easy to put it in. All right, so if you go back to our tutorial on this, you realize that it's always the same approach. The gain is always the pass band gain minus the frequency specific gain. Okay, the pass band gain is basically the active component, right? That means if I put in inverting or non-inverting amplifier, then I amplify the signal. All right. So if you don't have a active component, then you just assume there is 0 dB. That means you take it as it is. Then what is left is only the frequency specific gain. And the frequency specific gain formula is fixed. Whether it's low pass, you have one formula, high pass, you have another formula. So for low pass, basically all you need to do is you plug it into the formula that says that 1 plus omega RC square at at frequency equals to 4000 must be equals to negative 18. Okay, then from there the rest is just solving it every day. Okay, 10 to the power of 18 by 20. Okay, and then you will get omega RC is equals to 2 pi 4000 RC, which implies RC will be equals to 3.14 times 10 to the power of minus 4 seconds. Okay, and then you just need to see which combination gives you this. Okay, and then you will see that is option B. Okay, so it's exactly the same things that we did in the tutorial. Okay, the same things. As long as you know which formula to use and how to put in the numbers, then you should be fine. Okay, question 23. Question 23 is very similar. Okay, so let me just draw out the spectrum first. So what you have is the signal that you want, okay, is here to here, which is 195 to 540, and the noise, okay, the noise that you do not want is in the range of 8,000 to 13,000, so somewhere here. Okay, so it's 8,000 to 13,000, and we want the noise to be reduced by 15 dB. Okay, that means when I design my filter, it must be such that, okay, at this point to this point here where I touch the 8K, I must go down by at least 15 dB. All right, so it's the exact same formula, minus 20 log to the base 10 of 1 plus omega RC square, in this case at F is equals to 8,000, will be equals to negative 15. Okay, and the rest of it is exactly the same, so you eventually get RC is 1.1 times 10 to the power of minus 4 second, and then you relate it back to this, okay, as the combination that gives you that. Okay, so again, very similar to the earlier question and what you've also seen before. Okay, question 24 is also the same thing. Only difference is it is a high pass filter. Okay, it's high pass filter. So if you look at the information given, okay, what you want, okay, is in the higher frequency range, okay, which is here 600 to 6,000. Okay, and what you do not want, the noise is in the range of 25 to 60 hertz. So the noise is somewhere here, 25 to 60 hertz. And what I want is the noise to be reduced by at least 14 dB. So the response of the frequency must be something like this. Okay, and if I were to extend this, that means from the point or the pass band till I hit 60, here to here must have gone down by at least 14 dB. That means when I hit 60 hertz, I should have gone down by at least 14 dB. Okay, that is the only thing. So the formula is almost the same. All you need to do is the 1 over RC is written differently. So what you have is 1 plus 1 over omega RC. Okay, so this is also given in your lecture, in the tutorial, okay, the last tutorial. Okay, and the rest is exactly the same. You just solve it. Okay, then from there you get RC is equals to 5.4 times 10 to the power of minus 4 seconds. Okay, and from there you will get the value of the option of this. Okay, so that is your high pass filter. Okay, and that is the last question on that. So the rest of the questions are on the sensor interface. Okay, so if you look at this question here, we are given a LM35 temperature sensor to detect the water boiling. All right, and what we are given is at 0 degrees Celsius, the voltage is 0 volt. Okay, and it increases by 10 millivolt per degrees. That means when I hit 100 degrees Celsius, it will be 100 times 10 millivolt, which equals to 1 volt. Okay, so as far as my sensor is concerned, my LM35, okay, what I want to detect is 100 degrees Celsius, and 100 degrees Celsius, I will output a value of 1 volt. Okay, and what I want to do is I want to design a amplifier circuit so that after I pass through with a particular gain, I'm able to generate the cutoff signal, which is 3.3 volt. Okay, so I want to generate a 3.3 volt as a cutoff. Okay, so currently the cutoff is at 100 degrees Celsius, which is 1 volt, and I want to make it 3.3 volt. So the gain is 3.3 over 1. Okay, and since I want a non-inverting amplifier, so it'll be 1 plus RF over RI equals to 3.3. Okay, and then you get RF over RI is equals to 2.3, and that, okay, so once you know this, then you need to see which combination gives you that. So that would be answer C. Okay, next question 26. Okay, so we are supposed to test a IR sensor for proximity sensing using the indirect incidence. Okay, and what you want is you want to figure out the circuit to activate one of the LEDs based on a distance of 4 centimeter. Okay, so the first thing is we need to see what does 4 centimeter relate to. So 4 centimeter here, okay, will relate back to 3.6 volts here. Okay, we relate back to 3.6 volt. So what you want to do is we want to compare with 3.6 volt. Okay, I want to compare with 3.6 volt. So the reference voltage, okay, so if I look at this op-amp here, the reference voltage for both of them is through the R1 and R2. So I have a plus 5 volt, and I have R1, and I have R2, and what I want is this point here is your Vref must be equals to 3.6 volt. Okay, which means that this combination R2 over R1 plus R2 multiplied by 5 must give me 3.6 volt. Okay, so once you understand this, then you need to see which combination of R1 and R2 will be feasible. All right, so you can see that a value of R1 equals to 2.7K, okay, and R2 equals to 6.8K, the two possible answers. Okay, so either B or either D, correct? Because both of these combination, both these options have R1 as 2.7K and R2 as 6.8K. So both of them will give me a reference voltage of 3.6 volt. Okay, now let's look at the op-amp. Okay, so we just look at one of the op-amp first. So let's, okay, so what we want is okay, so one of the op-amp must light up, okay, when it's lesser than 4 cm. If not, the other op-amp will light up when it's greater than 4 cm. So what we need to do is figure out which of these statement is correct. Is it LED1 light up when object is less than 4 cm, or LED2 light up when object is less than 4 cm? Okay, so we can just examine one of the LED. Okay, so let's just take LED1. Okay, so if I take LED1, the op-amp connected there, so we can see that the plus is connected to the reference voltage, which is 3.6 volt. Okay, and the negative is connected to my Vout, which is from the sensor. Okay, now let's look at a scenario. Okay, if I say that my 3.6 volt is greater than my Vout, Okay, so this is a comparator, and I'm connecting my LED over here. Okay, so if this condition is true, 3.6 volt is greater than V out, then my LED 1 will be on. Correct? LED 1 will be on. Now let's relate this condition back to the graph over here. So if my V out is smaller than 3.6 volt, that means I'm somewhere over here. Right? That means I'm somewhere over here, which means that my distance is smaller than 4 cm. That means my distance is smaller than 4 cm. All right. So if I look back here, the statement here, only LED 1 lights up and object is smaller than 4 cm. If not, it's LED 2. So this is the correct statement. All right, because when my distance is smaller than 4 cm, then my LED 1 will light up. All right. So that is how you analyze it. So if you do the same thing for op-amp 2, also you'll get the same thing. Okay, you get the thing that if the distance is greater than 4 cm, then the LED 2 will light up. Okay, so that is your question 26 here. Okay, question 27. Okay, so question 27 is more tedious because you have 3 circuits to analyze. All right, and what is the condition given is LED 2 to be lit when an object is more than 5 cm. Okay, so let's look at the important condition first. So the distance is greater than 5 cm. Okay, what we want is LED 2 to be on. Okay, so since we are interested in 5 cm, okay, you can see that 5 cm here relates back to 3.8 volt, around 3.8 volt here. All right, and if you look at all the 3 circuits, the voltage divider is 100 and 330, 100 and 330 for all 3. Okay, which means that the reference voltage, okay, is already set at 3.8 volts. So this is your reference voltage. So you're comparing against this to know whether you have hit the 5 cm mark. So let's look at circuit A first. Okay, so let's look at circuit A and examine just one of the LED. Okay, since we're interested in LED 2, let's look at LED 2. So if I were to draw LED 2 over here, so LED 2 is the plus is here, minus is here, and the plus is connected to my reference. No, plus is connected to my V out. Okay, so this is for my LED 2. So let me draw LED 2 here. Okay, and your minus is connected to my reference voltage, which is 3.8 volt. Okay, now let's look at this. For my LED 2 to light up, okay, for my LED 2 to light up, I must make sure that V out must be greater than 3.8 volt. Then my LED 2 must be on. Okay, so if my V out is greater than 3.8 volt, that means I am in this higher range, which equates to a greater distance. Correct, a greater distance. So this is correct. So circuit A actually satisfy my condition. Okay, so of course you can also go and confirm for the other op-amp, okay, to check whether LED 1 also lights up for smaller than 5 cm, which you will see it's true. Okay, but this already confirmed that for circuit A, when my distance is greater than 5 cm, my LED 2 will be on. Okay, because VR greater than 3.8 volts is equivalent to distance greater than 5 cm. Okay, they're both the same here. Okay, so circuit A is working, okay, based on our requirement. Okay, so now let's look at circuit B. Okay, let's look at circuit B. Now for circuit B, what do we have? We have dual supply op amp. Okay, dual supply op amp. So let me draw it here. Okay, so you have plus 8 and negative 8, and you have this connected to a positive terminal connected to the 3.8 volt, and your negative terminal connected to the Vout. Okay, and then you have two LEDs. Okay, so this is your LED 1 and this is your LED 2. Okay, so let's look at the analysis of this. Okay, if my 3.8 volt is greater than my Vout, okay, then what happens? That means your V plus is greater than V minus, and this will cause you to go to plus V set, which means your LED 1 will light up. Okay, because when I go to plus V set, I will forward bias this LED, so the current will flow through LED 1 and light up. Okay, in this condition, 3.8 volt greater than V set is equivalent to saying that your 3.8 volt greater than V out means your V out is smaller than 3.8 volt, means I'm here. That means my distance is smaller than 5 cm. Right, so your distance is smaller than 5 centimeter. All right, now the other condition where your 3.8 volt is smaller than your V out, that means your V out is greater, which means your V plus is smaller than your V minus, and this will cause your op amp to go to negative V set. So if it's negative, what will happen? The current will flow from 0 to negative voltage through this way. So I'll forward bias the LED 2. So my LED 2 will light up. And if my V out is greater than 3.8 volt, that means my distance is greater than 5 centimeter. Okay, so you can see that now I also satisfy the conditions laid out, okay, in the question. That means circuit B also is correct. Okay, circuit B is also correct. Okay, now let's look at circuit C. Okay, so for circuit C, okay, what you have is you have your op amp. Okay, your positive terminal is connected to 3.8 volt. Your negative terminal is connected to your Vout. Okay, and your output terminal of op amp is connected, okay, from 5 volt here to resistor, LED 1, LED 2. Okay, so this is your LED 1 and LED 2. Okay, now let's see what is going to happen. If my 3.8 volt is greater than your V out, okay, so this is also a dual supply, correct? So KC is also a dual supply. So I have a plus 8 and negative 8. Okay, so when your 3.8 volt is greater than your V out, okay, then what happens? I will go to plus V set. Okay, so that will allow my first circuit to be forward, LED 2 to be forward biased. Okay, now this is already wrong, correct? Because your LED 2 should only light up when your V out is greater than 3.8 volt. That means greater than 5 centimeter. Okay, so this is already wrong, so you know it's not correct. Okay, but if you take the other situation, 3.8 is smaller than V out. Okay, which means you will go to negative V set. But when you go to negative V set, your current also cannot flow in the opposite direction because your LED is reverse bias. LED 2 is reverse bias. Okay, so no LED will light up. Okay, so this circuit C is not going to work. Okay, so the only two circuits that are going to work are circuits A and B. So that's why the answer here is B. Okay, so this question is quite tedious, correct? Because you really have to analyze all three circuits, okay, before you can actually answer. Okay. Okay, so we are in the last three questions. Okay, question 28 is again interfacing with sensor. So what we have is a humidity sensor, and we want to be able to connect it to an Arduino, okay, with a range of 0 to 5 volt. All right, so what we have is so what we want to do is we want to amplify the signal before we do the A to D conversion. So before we amplify, so what we first need to know is from the sensor itself, what is the maximum voltage I can get? Okay, so the maximum voltage I can get is, okay, so the maximum V out is when I am at 100% humidity. So it will be 5 multiplied by 0.00474 times 100 plus 0.2354. So that will give me 3.547. So that will give me 3.547 volts. And what I want to do is I want to take this and pass it into an amplifier with a gain. And what I want is, since your Arduino ADC range is 0 to 5 volt, you want to maximize this all the way to 5 volt. Okay, so the gain that you want is in essence 5 over 3.547, which will be 1.41. Okay, and since it is a non-inverting amplifier, so it's 1.1 plus RF over RI will be equals to 1.41. So RF over RI will be equals to 0.41. Okay, and then going through all the combination, you will see that the B is the answer that gives you this gain, RF over RI of 0.41. Okay, question 29. So in question 29, we are trying to detect the pH, okay, range, okay, of 7.4 as a safe range to make the water drinkable. All right. So what we want is to detect the range of pH value between 7 and 8. So this is the range that we want. Okay, this is the pH value and this is the voltage. Okay, so if you look at the response, okay, if you will draw the response curve for this, you'll notice that your graph looks something like this. Okay, where this is your 7, okay, because at 7 your voltage is 0. Okay, when it is before 7 it is positive, and it's after 7 it is negative. Okay, and the values we are interested in is somewhere here, 7 to 8. So these are the values we're interested in. Okay, these are the voltage values. So since it is a negative range, okay, before we can sample it with Arduino Uno, we need to make it positive. Right, so definitely we need a inverting amplifier to make it positive. So it's either B or C. All right, and if you look at the values, all right, the gain for C is higher, so that is a more appropriate option, okay, for this scenario here. Okay, so using option C with a higher gain and an inverting amplifier, you'll be able to get a better reading, okay, to identify the pH value that you're measuring. Okay, so that is that. Let's go to the last question here. Okay, so this last question is interfacing sensors, okay, to achieve an objective, which is to turn on the lights and fans based on the LDR value. Okay, so if you remember your LDR response, okay, it will generally be something like this, where as the intensity increases, light intensity increases, the resistance goes down. Okay, and what you want to do is you want to detect the room temperature of 25 degrees Celsius. Okay, you want to detect a room temperature at 25 degrees Celsius. Now, what we know is the output of the LM35 increases by 10 millivolt per degrees, and the output is 0 volt at 0 degrees. Okay, so for the LM35, okay, when it is detecting 25 degrees Celsius, I will be getting 25 millivolt, okay, which is 0.25 volt. Okay, now so for a 0.25 volt, all right, I am going to amplify it, okay, through this first op-amp over here, okay, to provide, okay, to provide the voltage that is necessary to compare with a reference point here. So this is going to be a reference point. This is going to be a reference point. So what I can do is I can set my R2 and R3. So if you look at R2 and R3, okay, what you will notice is all the R2 and R3 values over here are equal. Okay, that means if R2 is 470, R3 is 470, 330, 330, and so on. Which means that this voltage here at this point is going to be half. That means it is 2.5 volt. Okay, that means the reference voltage that I'm comparing against is going to be 2.5 volt, which means that I want to amplify this signal all the way to 2.5 volt. That means it's a gain of 10. Okay, and since I have a non-inverting amplifier configuration, I know that 1 plus RF over RI must give me 10. So RF over RI will be 9. Now when RF over RI is 9, then you can say that the two possible answers will be B and C. Okay, B and C. Now, so what happens? So when I look at this op-amp over here to turn on the motor, so you'll notice that over here, my negative is connected to the 2.5 volt. And this positive is connected to the LM35 multiplied by 10. Okay, so if my temperature goes up a bit, so let's say my temperature is 26 degrees Celsius, which means it is 2.6 volt. Okay, that will happen. At the output side, I will on the fan because V plus will be greater than V minus. So I'll have a positive V set, which will on the fan. If my temperature goes low a bit, 24 degrees Celsius, that means it's 2.4 volt, then I will off the fan. Okay, so that is how this whole circuit is going to work. All right, now for the LDR part, all right, now the key thing is the only difference between option 2 and option 3 is your R1. All right, and the value of R1, okay, one is in the mega ohm range, the other is the kilo ohm range. Okay, so if you, this one requires you to remember what you did for your studio. So if you look back at your studio, you'll notice that the value of R1 should be approximately 100K, okay, around there. So which means that the option that is closest is option C. Okay, so that is how you get the final answer here. Okay, so that basically wraps up all the questions that we have in this revision set. Yeah, so that's all. I think if you have any questions that you want to discuss further, please ask me now, okay, and then we can discuss them. Okay, for question 29, why do we choose C over B? Because C has a higher gain than B. Okay, so both of them are similar except that C has a higher gain, which means that you get a better accuracy for the ADC conversion. Okay, if you are on MC, okay, if you are MC for this Saturday, okay, you just need to make sure you have a valid MC, and you will have a makeup. Okay, similar to the first quiz as well. Those who missed it also had a makeup. So if you are on MC, just make sure you have an MC. All right. If you are COVID positive, you still need to update in the Universe app and show that you have updated it. Okay, but other than COVID, if you are on MC, then you just need to make sure you produce a valid MC. Okay. Okay, for question 30, solving R4. Okay, R4 doesn't. Okay, R4 is basically the brightness of the LED. Correct. So 330 and 220 in both cases will not have much of a difference in terms of the brightness of the LED. Okay, because you are biasing the LED. So okay, so of course if you have one in the kilo ohms or mega ohms range and one in the ohms range, then definitely you will take the one in the ohms range. Okay, because if you take something that is too high of a resistance, then your LED will not have much brightness at all. Okay, okay, when to use inverting amplifier? Okay, I mean generally you will use inverting amplifier. Again, if you look at this kind of scenarios, the use of inverting amplifier is if your signal that you get is negative, and if you are using the amplifier, or if after the amplifier you want to do some A to D conversion or something like that, okay, or you are going to compare it with some positive value, like comparing with connecting it to a comparator, then you want to use a inverting amplifier to make sure that it's a positive value. Okay, so I think the two possible scenario is if you're going to do A to D conversion. Okay, that is one, because for A to D conversion you want all your values to be positive. So if your actual value that you're getting from the sensor is negative, then you want to invert it. Okay, the other scenario is if I'm passing the signal through to a comparator, okay, then maybe you may also want to invert it. Okay, again, depends on the scenario and whatever other information is given in the question. Okay, but A to D conversion, definitely you will want to convert it because your A to D converter will want positive values. So you want to make sure that the signal that you are going to convert is in the positive range. Okay, so as usual, I'll upload the video and I'll also send this document. All right, so you can use that for reference. Okay, so question 30 is relating back to the lab on the LDR. I think the second last lab, I think. The second last or the last lab, yeah. Okay, so I hope that all of you try your best and all of you come and finish up, okay, the assessment on Saturday. Okay, because basically once you're done with that, then you really have nothing else except to just focus on your robot and finish up your development work, okay, for the final assessment. Okay, so any other questions? Okay, if other questions or what, you can still feel free to email or WhatsApp me, okay, today or tomorrow, okay. Yeah, I will upload the file by today. Okay, so thank you everybody. Bye.